So this is all I have to say for now about the different kinds of Lie algebras in terms of the structures. The next thing on my list is I want to talk about the relationship between Lie groups and geometry. And this has a lot of application in physics and differential geometry and topology and stuff like that. Okay, so the next thing on my top list is Lie groups and geometry. Once I'm done with that, we will move to representation theory. If it turns out that we cannot really cover the minimum representation theory, I might ask for an extra 1 or 2 classes, which will not be examinable, but I just want you guys to kind of have the basic notions of representation theory. But for now, we're going to discuss Lie groups and geometry. Okay, so Lie groups have very important applications in differential geometry. I mean, I cannot emphasize how important they are. So differential geometry is the subject in which one considers the geometry of a manifold on which you can define differentiable functions, right? So this is a vast topic that deserves a course in itself. But here we just touch upon a few ideas. The first thing is we want to talk about the symmetry groups of manifolds. Okay, so we have already explored what a manifold is. So essentially, a manifold is an n-dimensional, say Mn is an n-dimensional topological space which admits local charts, which are subsets of Rn, right? We saw an example in a previous class where we took a sphere and then we found that all the points of the sphere except the North Pole can be projected onto R2 by the stereographic projection, R2 minus the point at infinity, right? And similarly, all the points on the sphere minus the South Pole can be projected onto R2 minus the point at infinity. So these are the charts. So this is phi 1, this is chart, this is phi 2. Charts are essentially local coordinates. Okay, so for S2, it should be clear that, so suppose we have an S2. So if I have any point on S2, I can represent that point by a unit. So suppose we have a S2 whose radius is 1, then we can represent that point on the surface of S2 by some vector R. So of course, if I now act on this vector R by a rotation matrix, I go to another vector R prime, But since it's a rotation matrix, that means it's an element of SO3. That means that the modulus of R and the modulus of R prime is the same, and that's 1 mod squared, right? That means that the action of SO3, we see this, this particular action, this is known as an action, I will define it. The action of SO3 on S2, it doesn't change itself. The resulting space looks exactly the same, right? It's a symmetry. So we say that SO3 is the symmetry group of S2. So I'm trying to be very, very heuristic here. I'm just trying to give you the intuitive idea. And we'll pin down the details later. Okay, so I think there are some questions that I haven't noticed yet. So let's see what they are. Yeah, if you have to leave, don't worry. Yeah, okay. All right. All right, so any questions so far? We will be formalizing these ideas soon. Okay, let's now define, first of all, what do we mean by a group action on a manifold? Intuitively, what I'm trying to say is that if I take a globe and I rotate the globe around any axis that goes through its center, that globe is just going to look like itself. So therefore, the rotation group should be the symmetry group of the globe. But if I translate the globe, then of course the globe is no longer where it used to be. Then that is not a translation symmetry of the globe. Okay. So let's define the group action on a manifold. So let G be a Lie group and let M be a manifold. The action of G on M is the map sigma, which is a map from G cross M to M, such that the map must have these properties. The identity element of the group acting on a point P on the manifold must give me the same point for all P in the manifold. The other point, the other property it must have is if I have, so suppose I have a group action with G1 on a point and it gives me another point, and I have another group action on that resulting point, then that should be given by the group action of the composition of the two group elements acting on the original point. Okay, so this is a consistency, these are very, very natural properties to ask for. Okay, any questions about what is meant by the group action on a manifold? Okay, let me give you an example. So let, say, X be a vector in Rn. and say G be an element of say GL and R. Okay. Then the group action defined by G acting by matrix multiplication on X is a group action. And you can verify that it satisfies these two properties, okay? Okay. Now, we could have defined the group action of SON on Sn minus 1. And let me give that to you as an exercise. So if X is an element of Rn such that the modulus of X squared is 1, that is, it forms an n minus 1 sphere, then show that G of X for all G in SON constitute a group action of SON on Sn minus 1. Okay. So if you can show this for S2 and SO3, you have shown this for essentially all. So this should be a red